So Exergy is the topic. This is our fourth and final before our exam on Exergy. And so there's a few topics that we still have not covered that are about the exergetic efficiency. Last time we talked about the exergetic efficiency of the turbine. It's not just finding an equation somewhere and then using it. It's actually understanding the equation that's really, really important. So you have a fluid stream that goes through the turbine. The fluid stream is giving up some energy, and then we try to convert that energy into useful shaft work coming out. In terms of exergy, you can view it as the fluid stream is giving up some exergy. And where do we want that exergy to go? We want that exergy to go to shaft power, but some of it through entropy generation, through irreversibilities, is destroyed. And so you can think of saying what comes out of the fluid stream would be mass flow rate times the flow exergy coming in minus the flow exergy going out. That's what's coming out of the fluid stream. It's either going to be converted into shaft. Notice that there's no heat transfer, hence there's no exergy transfer with our standard model of a turbine. If Q dot is not zero, then we could have exergy transfer with the Q dot going out of this turbine. But we're going to assume it's zero. And then the other place that it goes is that it's destroyed. And we'd like as much to go here and little to go there. So our efficiency, exergetic or second law efficiency for the turbine is defined as where do we want it to go? Divided by where it came out of. And let's jump on and go to the next topic, which would be of a compressor or a pump. Well, we have a fluid stream going through the compressor or the pump. How about compare the outlet flow exergy compared to the inlet flow exergy? Is the outlet flow exergy less than the inlet flow exergy, or is it greater than the inlet flow exergy for a compressor or a pump? It's greater. So what happens is, I know that the sign convention is we're going to leave this positive out, but actually that's going to be a negative power. Okay? So right away you say negative W dot. So what is that? That's the flow of exergy into the system. A negative of a negative quantity is a positive. That's a positive flowing into the system. All right. Where is it going to go? Well, it's not going to go out with any heat transfer. It's either going to be going out with the fluid flow stream or it's going to be destroyed. And so it either goes M dot, it's going to go out with the fluid flow stream. The flow exergy out is greater than the flow exergy in. That's where we want it to go. That's where we want it to go. And if it doesn't go there, because of irreversibilities, exergy could be destroyed. That's it. Now, if we did have a non-zero Q dot, we would have to include that as an out. Okay. Where do we want? We want as much of this to be converted to that and little to be converted to destroyed. So we have the definition of an exergetic efficiency for the compressor or the pump, and that would be how much gets to where I want it to go compared to what comes in. Now the heat exchangers, and there's two types of heat exchangers. One is a counterflow heat exchanger. Take it slow when you're introduced to heat exchangers. Have the hot fluid on the hot side and the cold fluid on the cold side. Which way is heat transferred within the heat exchanger? From the hot to the cold or from the cold to the hot? Hot to the cold. Go slow. You ask yourself simple questions and you'll save yourself a lot of painful errors and stuff like that. But this rate of heat transfer is within the heat exchanger from one fluid stream to the other fluid stream, from the hot to the cold. Now, what about out here? Typically, we have what we call an adiabatic heat exchanger. That is one of the oxymorons. It doesn't like, what? You know, jumbo shrimp. What? Jumbo shrimp? That's an oxymoron, right? It just sounds wrong. Adiabatic, like no heat transfer. Heat exchanger. What's the purpose of a heat exchanger? To transfer heat. It's like, no transfer heat exchanger. What? Anyway, the adiabatic heat exchanger says that with the surroundings, Q dot's equal to 0. So we have a large control volume, and for that large control volume, Q dot with the surroundings is 0. But every now and then, we'll have a control volume with respect to the hot fluid. That control volume with respect to the hot fluid stream is not adiabatic. There's a heat transfer out of the hot fluid stream, not to the surroundings like outside the heat exchanger, but within the heat exchanger to the cold fluid stream. And sometimes we'll do an analysis of a control volume around the cold fluid stream. So when you're doing a heat exchanger analysis, be careful of, is it just of the hot fluid stream control volume, cold fluid stream control volume, or both fluid streams and in the entire heat exchanger control volume around it? So what do we want? Well, from a heat transfer, we just want to promote heat transfer from the hot to the cold. There's really no isentropic efficiency for the heat exchanger. This is the first real heat exchanger efficiency we have in the whole textbook. It's the exergetic. So you have to scratch your head a little bit and you say, what is going on with this heat exchanger? Well, we have something coming out of the hot fluid stream. Exergy is coming out of the hot fluid stream. This is out of the hot fluid stream. Okay, where's it going to go? Once the ability to do work is transferred out of the hot fluid stream, where does it go? Into the cold fluid stream. Or where else can it go? Be destroyed. Right? So what's the equation for out of the hot fluid stream? Well, do this. Which flow exergy, compare 1 and 2. Compare 2 to EF1. Is it greater, equal, or less? The flow exergy coming out of the hot fluid stream at state 2 compared to EF1 coming in of the hot fluid. You're right. How did you do that? What were you thinking to be able to get that right answer? You're thinking of exergies very closely linked to energy, and definitely the energy is coming out of the hot and going to the cold. Hey, so it's taking with it some of that exergy. Or you could think of it, this Q dot's coming out of the hot, and if you multiply that by 1 minus T naught divided by TB, I know TB usually is not constant, but that's an idea of some percent of the Q dot, which can be represented as the flow of exergy with the Q dot. So that's coming out of that hot fluid stream. There's a couple ways to think of it, but this is the correct relationship. So the mass flow rate of the hot fluid times the EF1 minus EF2. That's what's coming out of the hot fluid stream. Let's do the discussion of the flow exergy for the cold fluids now. The cold fluid outlet flow exergy is 4. Is that greater than, equal to, or less than EF3? It's greater. Same type of logic. The energy is increasing of the cold fluid stream, and exergy is increasing. So what you would like to see is everything out of the hot gets into the cold. Well, M dot cold EF 4 minus EF3. But if it doesn't go there, and on the heat exchanger, almost by definition is irreversible. There's a lot of entropy generation in them. So what are you going to get? You're going to get the destruction. So you can think of a efficiency for the second law efficiency for a, I don't know what you call it, counterflow heat exchanger, and that would be how much went into the cold fluid, m dot cold EF4 minus EF3, divided by how much came out of the hot, m dot H times EF1 minus EF2. Will it be close to 100%? No, forget it. Again, heat exchangers often are very irreversible. So I'm not a great fan of exergetic analysis of heat exchangers. It's maybe not as insightful. You just know that heat exchangers often are an area where the design engineer wants to improve and has an opportunity to improve the efficiency of the overall system. Basically make small delta T's. Small delta T's to drive the same Q dot. And that's going to, so you can minimize it, that's going to help with efficiency. Make sure they get in the stack, okay? So she can just kind of pick them up 15 minutes after class, or 10, 15 minutes after class starts, and then go. Did you have any other announcements? The homework grade from the homework 1 is posted on Blackboard Learn? Grade book?
Trying to get it.
She's going to work with me on it. She looks stressed because it's a lot of work. Thank you. All right. Second law, exergetic efficiency for a different type of heat exchanger, a direct contact heat exchanger. All you're doing is mixing a hot fluid stream with the cold fluid stream, and you're creating a warm fluid stream. How's that for terminology? Okay, they're not separated by a boundary, so they actually mix. Okay, well, what do you have here? The way to think of it is to think of the hot fluid stream is going all the way through, and the cold fluid stream is going through, and they mix to create the warm fluid stream. But conceptually, think of m dot 3, because m dot 3 is definitely equal to m dot 1 plus m dot 2, isn't it? And so the flow of exergy going out at state 3 is equal to m dot 3 times EF3, which is m dot 1 EF3 plus m dot 2 EF3. Hey, that seems trivial. Isn't that the same? Yeah, that's EF3 and EF3 there, right there, the flow exergies at the exit. But here we see that m dot 1 continues through the system, and m dot 2 kind of goes, well, I wanted to change color there, through the system. So we can say for exergetic efficiency, something's coming out of the hot fluid stream. So what comes out of the hot would be modeled as m dot 1 times EF1 minus EF3. And it's going to go into the cold fluid stream. That's equal to m dot 2 EF3 minus EF2. Hey, the order is switched, isn't it? EF3 is first before EF2. Here it's second. It's after. It's got a minus sign. Well, hopefully you understand why. And then if the other part is that it's destroyed. And so here is an exergetic efficiency for a direct contact heat exchanger, and it would be m dot 2 times EF3 minus EF2, because you theoretically you'd like all that comes out of the hot to go into the cold, but some is destroyed. So m dot 1 times EF1 minus EF3. That exergetic efficiency makes sense? Again, I personally am not a big fan of it, although it's open fair game for exams. It's just they're trying to help you see that there's opportunities to improve efficiencies in heat exchangers in real systems. And that's definitely true. Did that help? Any other comment or question on this? You ready to solve a problem? We have air flows in a counterflow heat exchanger. Well, you have a kind of a quick sketch of a counterflow heat exchanger. Put the hot fluid going from state 1 to state 2, and you put the cold fluid going from state 3 to state 4. And we have air, and it comes in at 27 and 0.1 megapascal and exits at 22. From this information, it comes in, air comes in at 27 and goes out at 22. What's happening to the air? Is it heating up or cooling down? It comes in at 27 and goes out at 22. It's cooling down. Is the air the hot fluid? Yeah, take these steps slowly because it's very tricky. So just by knowing the temperature goes down of the air, we know that it's giving up some heat. It's transferring heat out of the air. Air is the hot fluid. So air, let me just kind of put it up here. Air is hot. H-O-T. I can spell. Try that again. A-I-R equals to H-O-T. I'm really challenged. Okay? All right. So it comes in, and you can put in T1 is 27 degrees C. If you needed to convert that right away to Kelvin, what would it be? 27 is? 27 is how many Kelvin? 300 Kelvin. And it goes out T2 of 22 degrees C. What is that in Kelvin? 295 Kelvin. It was a 5 degrees C as well as a 5 degree Kelvin temperature decrease of the air through the system. It comes in at 0.1 megapascal. What is that in kilopascal? 0.1 megapascal is how many kilopascal? 100. How many bar is that? Very good. You're going to be ahead of everybody else. How many times do I see an error in just converting between megapascal, bar, and kilopascal on exams? Just kind of get it down, right? All right. That's good. You got it. So we're looking at basically a 1 bar, 0.1 megapascal. Let's continue to read. Refrigerant 134A, hey, that has to be the cold fluid. It enters at 4 bar, so the pressure is 4 bar. And quality of 30%, X equal to 0.3. And a mass flow rate's given. M dot of the refrigerant is given to be 35 kilograms per hour. Refrigerant exits at 10 degrees C, so T4, 10 degrees C. Stray heat transfer is negligible, meaning it's an adiabatic heat exchanger. No heat transfer where you don't want it to go, which is in the surroundings. And there is no significant change in the pressure for either stream. So if P1 is equal to P2, because inlet outlet, there's negligible pressure drop for the air. And so that's equal to 1 bar, right? And here I'll just write it down here. P4 is equal to P3, which is 4 bar. This was P3, that's X3. All right. Let T0 be 22 degrees C, so 295 Kelvin for the dead state temperature, and P dot be 1 bar for the dead state pressure. Ignore the effects of motion and gravity, so no kinetic and potential energy effects. Part A, for the refrigerant stream, determine the rate of heat transfer. Well, how would I do that? What exactly am I asked to solve for, and then how do I solve for part A? Q dot. Yep, it's Q dot. And so it's Q dot into the refrigerant stream, true? So we know that it's out of the hot air stream. So maybe you want to think of maybe having 3 Q dots, but they're all equal. So you could have that Q dot, which is out of the hot, is equal to Q dot that's into, so maybe I say out of the hot, and into the cold, or just call it Q dot. It's just, okay, how are we going to solve for Q dot into the cold refrigerant stream? Do a control volume either around the hot fluid or around the cold fluid. And so if we do an analysis of the hot fluid, we may be able to tell what comes out of the hot fluid. That's what goes into the cold. Or if you do a control volume analysis around the cold fluid stream, the refrigerant stream, what comes into it would work. Okay, let's do for the hot fluid, and it's an energy balance for this control volume, right? So what do we have? We're going to have that the mass flow rate of the hot fluid times the enthalpy 1 minus enthalpy 2 is equal to what is transferred out of the hot fluid. Is that a good first law? The other professor who likes to teach, who does a very good job, Dr. Creamy, he requires all the students to start from the most general, but I'm fighting for inches and millimeters of space right here, and I don't want to click to a new page. I encourage you to start from the most general equation and know why this term is 0 and that term is 0 and not in this part or right here, and then why you get this. Otherwise, what students do is, oh great, another equation to memorize. Nope, you don't need to memorize. Start from the most general, apply it clearly, and you'll get in this equation. How many people like that equation? Do you understand it? Does it make sense? Okay, so if we're trying to calculate Q dot, can I get H1 and H2? Can I get this H1 right here? What is the fluid? Air. And it's at a temperature of 300 Kelvin. Can I get the enthalpy of air at 300 Kelvin? And a lot of you are doing exactly what you're supposed to do. You're seeing if you can find it in the textbook appendix. So what do we have? What table do you think you'd like to go to? Table A22. Table A22, and you can look up the enthalpy at 300, and what do we get? What is the H? 300.12. Yep. So it's 300.19 kilojoules per kilogram. Likewise, you can get H2, and H2 at 295 is 295.17 kilojoules per kilogram. So both of those are known. That's good. How about the mass flow rate of the hot fluid, mass flow rate of the air? Do we know that? We're given the mass flow rate of the refrigerant. Are we given the mass flow rate of the hot air? All right. Leave that work. Go to another control volume. Now do the control volume of the cold fluid. And what would that read? The mass flow rate of the cold fluid times the exit enthalpy minus the inlet enthalpy of the cold fluid is equal to the rate of heat transfer into the cold fluid. That's the same Q dot. Let's try this. Can we get the enthalpy at state 3 for the refrigerant? How would we get the enthalpy at state 3 for the refrigerant? You have the quality, and you have the pressure. It's 4 bar. So we look at the refrigerant table, and what is the equation? Oh, isn't it going to be, let me make some more room here. H3 is equal to HF at 4 bar plus the quality at state 3 times HFG or HG minus HF. I need the saturated liquid and the saturated vapor enthalpy for refrigerant 134A at 4 bar. So luckily we don't have to interpolate for that part, and we find that it's 62.00 plus the quality 0.3 times, and I'll just put in the number which is HFG, 190.32. And so H3 comes in at 119.06 kilojoules per kilogram. Thumbs up, you like that? All right, do this. H4. What is the pressure at state 4? What is the temperature at state 4? Well, can you find the can you find the enthalpy of the refrigerant exiting that heat exchanger? I'm going to pause and walk around and see how many people can find it. So we get better at identifying the condition of state. What is state 4? How would you describe it? Subcooled liquid, two-phase, liquid vapor mixture, or superheated vapor? Slightly superheated vapor, right. And so from the superheated tables you get that H4 comes in at 253.35 kilojoules per kilogram. And so we have the H3, the H4. We also have the mass flow rate of the refrigerant, the cold fluid. It's 35 kilograms per hour. We can calculate Q dot from this equation. So we calculate Q dot, and it comes in at 4700 kilojoules per hour, and we box it. That's the answer to part A. For the airstream, evaluate the change in the flow exergy rate for part B. Okay, we want the change in the flow exergy rate in the same units of kilojoules per hour. So what are they asking for part B? I'm sorry, I'm going to have to speed up a little bit. I really wish I could just give you more time because you've got to do this yourself, right? Basically, they're asking you to solve for the flow rate of flow, the change in the flow exergy rate. Well, it's coming out of the airstream at state 2 greater than it went in at state 1. That's just mass flow rate times EF2 minus EF1. That's the mass flow rate of the hot fluid, the air. And so you say, what's the mass flow rate of the hot fluid times H2 minus H1 minus T naught S2 minus S1. True or false? Doesn't that look good? Okay, so we already know how to get these H's. We looked them up in table, the air table. How do we get the change in the entropy? I have to scroll down a little bit, sorry. So this will be equal to the mass flow rate of the hot times H2 minus H1 minus the dead state temperature times S2 naught minus S1 naught minus R natural log of P2 divided by P1. Do you understand that equation? Do you understand that equation? And luckily for us, the pressure hasn't changed. The inlet pressure has not changed. So what is the natural log of P2 over P1 if P2 is equal to P1? 0. The natural log of 1 is 0. So this whole term, thankfully, simplifies. And in that case, it is simply the difference in the S naughts that come straight out of the air tables. That's an extra column in the air tables. So let me do this. The EF2 minus EF1, the difference in the flow exergy rate for the airstream is evaluated, and it comes in at negative 37.8 kilojoules per hour. Talk to me a little bit. Why is it negative? It's the air, it's the warm, it's the hot. Stuff is coming out of the hot. The heat transfer out of the hot. It's going to have an enthalpy decrease, an energy decrease. It's going to have an exergy decrease. Right? That's why there's a negative sign on it. All right. For the heat exchanger, evaluate the exergy destruction rate for the heat exchanger. So first we had two streams. Now we have for the heat exchanger. How do I calculate that? How would I calculate the exergy destruction rate? There's two ways to do it. You can do an exergy balance, get it directly. Let me show you the equation. I'm sorry, I have to scroll down. The rate of exergy destruction will be basically you could write it a couple different ways, but let me try it this way. The mass flow rate of the hot and then EF1 coming in plus the mass flow rate of the cold times EF3. Aren't those two coming in? And if nothing went out, all of that would be destroyed. But we have going out minus the mass flow rate of the hot times EF2. And we have going out EF4 there. Maybe I should use the same bracket or something. Does that equation make sense? And what was this that we just calculated? Minus the change in the flow exergy rate of the hot fluid stream. And then this is going to be the change in the flow exergy rate of the cold fluid stream. It's kind of like, well, why is there a minus here and a plus there? Well, just do the math. So we're going to have a minus 37.8 kilojoules per hour. And then what we have for the change in the cold, it's going to pick up EF4. Actually, this is kind of a crazy one. It'll be a plus a 214.9 kilojoules per hour. And the way you do that is you have to go back and get the flow exergies, getting the entropies out of. So this right here is H3 minus H4 minus T naught times S3 minus S4 out of the table, the superheated table. And so what we find is the exergy destruction rate is a whopping 253 kilojoules per hour. This is one of these examples where the definition of the exergetic efficiency for a counterflow heat exchanger doesn't make any sense at all. And if you want to explore this, what I would encourage you to make more sense out of this problem from an exergetic point of view is put the dead state temperature below any temperature in the heat exchanger. Currently, our dead state temperature is 22 degrees C, isn't it? And what about our temperature of the refrigerant coming in? That temperature at 3 is the saturation temperature of the refrigerant coming in. It's like 8.9 degrees C. Compare 8.9 degrees C to 22 degrees C. It's cold, right? Likewise, it goes out at 10. It's cold compared to 22. So at this point, to make more sense of, from an exergetic perspective, that dead state temperature I would set to like negative 40 degrees C and redo it. It'll make sense then. Right now it really doesn't make sense. In a way it does make sense, but look at what is this? answer for part B. It's what's coming out of the hot. More is being destroyed, if I scroll down again, more is being destroyed than what's coming out of the hot. That's why it doesn't make sense. All right. In the interest of time, I leave that with you and I press forward, okay? So we have steam. Its flow rate is 0.3 kilograms per second. It flows through a throttling valve. This is our traditional symbol for a throttling valve. This is one of those devices, inlet to exit, that you need to know a little bit about. Is there any Q out of the throttling valve? No. Is there any shaft work out of the throttling valve? No. So Q dot and W dot are equal to 0. And we do a first law analysis around this control volume around the throttling valve. Even though the pressure is lower than the inlet pressure and the temperature is not necessarily the same, it's typically, not always, but typically lower as well. We find that typically the specific volume is changed, that property's changed, and it typically goes up. And the enthalpy is the key property. What do we do when you get that out of the first law analysis around a control volume for a throttling valve? Another thing to memorize? No. Another thing to know by being able to apply the first law for that problem. It's constant enthalpy. It's isenthalpic. Do you know that? That doesn't come out of this chapter, this course. It comes out of the prerequisite course. True. What about the entropy? Typically, it's very irreversible. It is irreversible. S2 is much greater. So you have to know what's a throttling valve. So it comes in at 320 degrees C and 60 bar, and it goes out P2 20 bar, and determine the rate of exergy destruction in the valve. How would I like to calculate that? Probably, if that's the first thing you need to do it this way. Calculate the entropy generation, multiply by the dead state temperature in Kelvin, and you got it. So, to solve for part A, I do a second law analysis. The second law for that same control volume would allow me to say that the entropy generation, the rate of entropy generation, is equal to the mass flow rate times S2 minus S1. There's a lot of work to get here. I'm skipping that step. I'm not encouraging you to skip it. I'm encouraging you to sit with the most general equation and get there. Now, how can I find that property S2? I can find S1 by knowing pressure and temperature. That fixes the state. It allows me to get H1 and S1. What about this one, S2? Well, you have to know that H2 can be decided because of the first law. So H2 and P2 fix the state. It gives me S2. So, boom, boom. Do they give me the mass flow rate? Sure enough, boom. And so we calculate that the rate of entropy production is so much, which I don't see it on my paper, but I do the exergy destruction by multiplying by T naught, and it's 40.6 kilowatts. How about for part B? Annual cost of exergy destruction, assuming 8,400 hours of operation per year, and the value of exergy is 2 cents per kilowatt hour. Well, you want the cost per year. That would be the cost per unit time times the time per year, or the hours of operation. So what is the cost per unit time? That's really the cost of the energy times the energy per unit time times the time per unit year. How's that? So what is the cost per unit energy? That was given up here. It's $0.02 per kilowatt hour. So what is the energy per unit time, or exergy destruction, I should say, per unit time? That's the 40.6 kilowatts. And then what is how many hours per year? That's the time per year. It's 8,400 hours per year. You see the kilowatt hours come together? They cancel with this one. and you get dollars per year, and the cost per year ends up to be $6,815 per year. Thank you for your attention. We're all done.